y squared minus 1. Okay? So, and what we want to do is to graph this. All right, so if we are going to graph this, okay, and I'm going to do my coordinates. So I have x that's coming toward me, y to the side, z going up. Okay, now I'm going to look at this. I notice that the formula doesn't have any x in it, so that means x can take on any value. So what I'm going to do, one thing I'm going to do is I'm going to extend my x-axis back to give me like the negative values. And I'm going to do the same thing with the y, and I'm going to do the same with the z. Okay, so what I'm going to do is I'm going to take a look at this, graphing this, okay, first. Okay, so z equals y squared minus 1. So it's going to be based in the y and z axis. Okay, so basically what this is telling me is that z, and if I look at this closely, it's going to be a parabola. So the lowest value on z is going to be -1, okay? And if you think of this is going to be a parabola that is going to open up. Now, as far as x is on the y-axis, as far as it's concerned, it's going to hit 1 unit on the positive and 1 unit on the negative, okay? So from 0, 0, 0, -1, we're going to go up toward the y-axis, up toward the y-axis. So this is what the graph would look like in just z and y. Now, since x is part of it, okay, and x can take on any value. So that means that we're going to create a plane, okay? And I'm going to follow this plane that is going to be parallel to the x-axis. So we're going to go up this way, and back, and back. So essentially what we're going to have throughout this whole plane is we're going to have a series of basically kind of, if you think of this, kind of a half plane, okay, that is going to be along the x-axis. Okay, any questions? All right, so let's look at the next example. So for the next example, we have this. We have 4x squared plus y squared is equal to 36. Okay, so if I take a look at this, basically this is void of what variable? Is void of z. So that means that we know that z can take on any value. So it's going to be along the z-axis. Okay, now what we're going to do first is to graph it in within these two variables. So if we're looking at it in terms of the xy plane, what would this be the graph at? So what would this be the graph of if we were just looking in the xy plane? Um, an oval is what it's going to be, but what is the technical name instead of an oval? Yeah, it's going to be an ellipse. Okay. So what we're going to do is to basically draw this ellipse. Okay. So set up our axis. Again, let's extend these back. This is X, this is Y, this is Z. Okay. So if I take a look at this, now I can take this and put it in standard form. So if I put it in standard form, that means that I can't have this coefficient of 4 on this x squared. So what I'm going to do is divide everything by 4. Okay, so I'm going to have the x squared plus y squared over 4 is equal to 9. Okay, sorry, I did that backwards. Since it's an ellipse, it needs to be equal to 1. So what I'm going to do is divide everything by 36. So I'm going to have x squared over 9 plus y squared over 36 is equal to 1. Better. Okay, so we know that the center of this ellipse is going to be 0, 0. Okay, because we don't have anything added or subtracted on the square terms. Okay, so next, under x, there is a 9. We take the square root, we get 3. So we're going to go 3 to the in a positive, 3 in the negative. And this is going to give us vertices on that. And then for under y, we've got 36. Take the square root of that, we get 6. So we're going to go 6 on y and 6 in the other direction on y. And that gives us the other two vertices. So essentially, this is our ellipse in 2 dimensions. Okay. Now, we said that z can take on any value, right? So that means that this ellipse will go up and down. Okay. And essentially what's going to happen here is that we're going to have other ellipses that are created along through this. Okay. So it's going to look something like this. Any questions? Okay. Let's look at the next example. So for the next example, we have this. We have that 4x squared plus 4y squared plus z squared is equal to 16. Okay. So if I take a look at this, all right, in this case, it's got all 3 variables in there. Okay, so one variable is not going to be infinite. So what we're going to do is take a look at how far are we going to be moving. Okay, so there's going to be some restrictions here. So let's take a look at our put our axis in. Okay, so what I'm going to do first is to take a look at the restriction on z. Okay, so what I'm going to do is to start off by, I'm going to let x and y both be 0. So if x and y are both 0, what values can z take? What's the maximum, what's the minimum value that z can take? Yeah, it's going to be 4, -4. So we can go up 4 units. So 1, 2, 3, 4. That's the high z is going to be. And we can also go down 4 units. That's the lowest z is going to be able to take. Okay, so now we got an idea of what's happening with z. So what I'm going to do now is I'm going to collapse this into the xy plane. So I'm going to make z 0. Okay, so let's see what's happening there. All right, so if I make z 0, okay, I'm going to end up with 4x squared plus 4y squared is equal to 16. So really, what am I dealing with here? So what is this an equation of? Yeah, it's an equation of a circle because we can divide everything by 4. So we're going to end up with x squared plus y squared is equal to 4. All right, now for the circle, it's centered at 0, 0, and it has a radius of 2. So we're going to go 2 on the positive side of y, 2 on the negative side of y, 2 on the positive side of x, 2 on the negative side of x. Okay, and this is going to give us our circle. Okay, so we have this. Now, so essentially what's going to happen here is that as x as z increases, okay, what it's going to cause is, what do you think is going to happen with the circle as the value of z increases? So as for this circle right here, as z increases, what do you think is going to happen as we pick higher, bigger values for z instead of starting off at 0? Well, let's think. If z is 1, that means I'm going to have 4x squared plus 4y squared plus 1 is equal to 16. Or I'm going to have that 4x squared plus 4y squared is equal to 15. So this is still going to produce an equation of a what? Yeah, it's still going to be a circle, but is the radius going to be the same size as the previous one? Yeah, the radius is getting smaller. Okay, so as we keep going up, basically we're going to get smaller circles. So essentially what's going to happen is that we've got our endpoints here that we've got marked on the x and y axis. So basically from z, we're going to have basically kind of an oval shape going here. And what it's doing is it's going to hit, and let me continue, there we go. It's going to end up kind of giving you basically a football shape, okay? And you're going to have circles that are going to go fill up in the inside, but you have to keep in mind as we approach toward a max of 4, okay, basically what it's going to do once it gets up to the 4, it's just going to create a point. In the same way, if it goes down toward -4, all it's going to do is create a point, okay? Because it's basically going to force this to be equal to 0, all right? So basically in kind of a freehand look, you have basically this shape here that is filled with circles, but they're getting smaller as you go up toward 4 and smaller as you go down toward -4. Okay? Any questions there? All right, let's look at the next example. So if we take a look at the next example, we have that z is equal to 8 minus x squared minus y squared. Okay. So what I want you to do is I want you to draw the piece that is in the xy plane. Okay. So if I'm having you to draw the piece that's in the xy plane, we're basically saying that z is equal to what? 0. Okay. So take a couple of minutes and do that real quick. Okay, so my question to you is that when you looked at the piece that's in the XY plane, what were you graphing? So for the piece that's in the XY plane, what are you graphing? Yes, it's going to be a circle. So if we take a look at that, okay, so if we take a look at that, we're going to have this. Um, Okay, so I'm going to put it in blue. So it's basically a circle that's going to be centered at 0, 0, and the radius is going to be the square root of 8. And you don't have to be exact on the square root of 8, so you're just going to kind of estimate what that's going to be. So 1, 2, 3, 1, 2, 3. It's close to 3, but it's not exactly 3. So a little bit 4, 3 in all 3 regions. And then we're going to connect. Now, this is going to basically count like a base. Okay. Now, so there's our base. All right. Now, if x and y are 0, that makes z what? So if x and y are 0, that makes z what? It makes z 8. Okay. So here's 8 up here. All right. So essentially what's going to happen is that from this point, you're going to have arches that are going to connect on the y. You're going to have arches that are going to connect on the axis. Now, those arches are basically hitting at the on those points that are we used to create the circle on the base. Okay? And this will be your 3D drawing. Okay. Any questions? Okay, let's look at our next example. So for our next example, we have 4x squared plus 9z squared is equal to 9y squared. So, okay, again, taking a look at this. So this is x, this is y, this is z. Okay. All right, so when we look at this, I'm trying to think of a nice way of doing this. Okay, so if we take a look at this, basically, say if x is 0, okay? So if x is 0, you'll have it 9z squared equals 9y squared. So basically, those would be equal to each other. So that will allow you to have basically this particular graph is going to go to the point 0, 0, 0. Okay, as one point that's going to happen. All right. Now, what we're going to do now, since this is equal to y squared, we know this is going to be opening on the y-axis. So what I'm going to do is create things that will help us, since it's equal to y squared, to open on the y-axis. So what I'm going to do, I'm going to say let y be, I want something that's going to work nice. Let's say y is 2. Okay, and I'm just trying to create something nice here so that we don't have crazy stuff going on. So if y is 2, we're going to have that 4x squared plus 9z squared is equal to what? Have it equal to 36. Okay. So essentially, what are we dealing? What is this going to be dealing with? A graph of? It's going to be dealing with a graph of an ellipse. Okay. But keep in mind that it's going to be in the XZ plane. Okay. So with that in mind, all right. So let's go 2 units on Y. So 1, 2. And then we're going to have this ellipse. Now the ellipse is going to end up being longer on X. Okay. And I'm just going to kind of freehand this. So it's going to be longer on X. And this is what we're going to have. Okay. But let's think about this. All right. I can get the same equation if y happens to be what other value? -2. So I'm going to essentially have the exact same thing happen when y is -2. I'm going to have this ellipse that's going to be formed. Okay. Now, let's think about this. As we move closer to 0, 0, what do you think is going to happen to this equation? So as we move on, keep in mind we're moving on the y-axis. And I'm starting at 2 and going in. So as I move in on y, what's going to happen to this equation? What's going to happen with the ellipse? Yeah, it's going to get smaller. So it's going to get smaller, and what's going to happen essentially is that we're getting smaller and smaller, but as we get closer to 0, 0, it's going to hit 0, 0. And it's going to hit it from both directions like that. And then as we go from 0 to 2, it's going to expand out and expand out. So it's going to kind of look like this. It's going to look like 2 cones where the vertex of the cones are touching each other, but they're along the y-axis. Okay. Now, keep in mind that this does go on infinitely on the y-axis. We're just condensing it down so that we can see a picture over a small window. Okay. Any questions? Okay, and let's look at the last one. So the last example we have is this. We have that y squared plus z squared minus x squared equals 1. Okay, so in this particular problem, this is kind of the oddball of the bunch, this minus x squared. So let's start off by just removing that term. So we're going to let x be 0. So if x is 0, that means we're going to have that y squared plus z squared equals 1. So essentially, we're going to start off dealing with what? We're going to start off dealing with a circle. Okay, so let's draw that. Now, it's going to be a circle in what axis? What plane? Yeah, it's going to be in YZ plane and it has a radius of 1. So, and let me switch colors here. So 1, 1, 1, 1, connect. So there's our circle. Okay. Now, we've got kind of a start. So what's going to happen here is that as x gets bigger or smaller, okay, and let's just do another one. So let's look at x is equal to, let's say 2. 2 is really not a good value, but it'll work for us. So let x be 2. So we're going to have that y squared plus z squared minus 4 is equal to 1, or y squared plus z squared is equal to what?
5.
It's equal to 5. Now, we're still focusing, if we take a look at this, we're still working with what?
A circle.
We're still working with a circle. So let's think about this. As x is getting larger, what's happening to these circles? They're getting bigger. And then same works the other way. As x gets smaller, what's going to happen to the circles? Be careful.
Bigger as well.
It's going to get bigger as well. And the reason why it's going to get bigger is because keep in mind that x is being squared. Okay, so it's always going to create this negative number that we're going to end up adding on to the other side. Okay, and we're going to be adding, so it's going to make it bigger. So essentially, what's going to happen here is that since what is happening is that we are essentially having kind of like hyperbolas going on here along the sides. And what's happening in the center is that the circles are getting bigger as we move along, but keep in mind that we're moving along the x-axis. Now, the only reason that we are able to, that it's going to look like this is because of the fact that we've got this negative x squared. Okay, if this was in plus, then all we will simply be dealing with was a sphere. Okay, so if the negative was in front of z, then this will be like this, but on the z-axis. If the negative was with the y squared, it would look something like this, but along the y-axis. Okay. Any questions? Okay. All right, so that is it with the section dealing with graphs. Okay, and you've got the homework problems. Basically, I'm not going to post any solutions to those. So what I'll do is I'll do the drawings on and I'll show them in class to you guys on Thursday. Okay. Any questions? Okay, so next, let's move into our next set of material, which is going to be dealing with vector functions and their derivatives. And let me upload that real quick. Okay, so taking a look at this, and I do want to show in this the file, the notes, because we do have several definitions and everything in there, and also I want to show you how a lot of the stuff that we are getting ready to do now relates back to what you've done in Calc 1. Okay, so starting off um, with the first definition. Okay, it says let um, R of t be equal to f of t in the I direction plus g of t in the j direction plus h of t in the k direction. Be a vector function, and uh, L a vector. Okay, we say that R has a limit L as t approaches t sub 0, and write it as the limit as t approaches t sub 0 of R of t is equal to L. Okay. If for every epsilon greater than 0, there exists a corresponding number delta greater than 0, such that for all t, we have that 0 is less than absolute value of t minus t sub 0 is less than delta, implies that absolute value of R of t minus L is less than epsilon. Okay, so if you take a look at this, all right, this corresponds to a definition you dealt with in Calc 1. So what definition does that look like in Calc and from Calc 1? And it's kind of staring at you. Okay, we're doing a limit. So if you look at this, this is basically the limit definition. Okay, so this is the delta epsilon definition for a limit. Well, we're now just translating this delta epsilon definition of a limit to vectors. Okay. Second definition. It says a vector function R of t is continuous at a point t equals t sub 0 in its domain if the limit as t approaches t sub 0 of R of t is equal to R of t sub 0. The function is continuous if it is continuous at every point in its domain. So basically, this is our definition of continuity. Okay, and it's looking like the first part is dealing with the pointwise continuity. The second part is just dealing with just continuity of a function. Okay. Next is that the vector function R of t is equal to f of t in the I direction plus g of t in the j direction plus h of t in the k direction has a derivative is differentiable at t if f, g, and h have derivatives at t. The derivative of the vector function r prime of t, same thing as saying dr dt, is the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t, which is equal to the derivative of f in respect to t in the I direction plus the derivative of g in respect to t in the j direction plus the derivative of h in respect to t in the k direction. So basically what it's talking about is that if we want to find the derivative of a vector function, we take the derivative of each of the components. Okay. Next definition is that if R is a position vector of a particle moving along a smooth curve in space, then v of t is equal to dr dt. So this is just basically reiterating back to dealing with physics. So if we are given a position function r of t, if we take the derivative of it, so we'd say dr dt, this becomes velocity. Okay. If we take the second derivative of position, which is the first derivative of velocity, that's going to give us acceleration. Okay. Any questions there? Okay, so just go ahead and I'm going to go ahead and finish up the rest. So saying that is the particle's velocity vector tangent to the curve. At any time t, the direction of v is in the direction of motion. The magnitude of v is the particle's speed, and derivative of a equals dA dt, where it exists is the particle's acceleration vector in summary. So for the velocity vector, it's the derivative of position. For speed, it's going to be the absolute value of, or the magnitude of velocity. For acceleration, it is second derivative of position, first derivative of velocity. Okay, and then in unit vector, you take the velocity vector over the magnitude of the velocity vector. Okay. Any questions? Okay, so let's look at the next page. All right, so the next page is kind of dealing with some definitions. Okay, and I'm gonna blow this up just a little bit so I can write in here. So for the first one, if I'm looking at the derivative rules for vector functions, so if I take the derivative in respect to t of a constant, it's equal to 0. Okay, so same kind of derivative rules. All right. Next, if I take the derivative in respect to t of a constant times some vector function. So basically what I can do is take out the constant and then take the derivative of the vector function. And sum rule, difference rule kind of go together. So if I take the derivative in respect to time of two vector functions added together, so u of t plus or minus v of t. So essentially what I will do is take the derivative of the first vector function, then add or subtract the derivative of the second vector function. Okay. Now, let's remember that with vectors, there's no multiplication and there's no division. Okay, so you notice here that in 5 and 6, we're going to talk about the dot product and cross product because those are vector operations. So keep in mind that we don't have a rule about multiplying two vectors together. Okay, and we don't have a rule for dividing two vectors. Okay, so for the dot product, and for the purpose of me running out of space, let me switch slides real quick. So for dot product, so if I take the derivative in respect to t of u of t dotted with v of t, basically what that's going to be is it's going to be the derivative of the first vector function dotted with the second plus the derivative of the second dotted with the first. Okay. Now, the cross product pretty much follows kind of the same format. So when I do the cross product, it's going to be the derivative of the first cross with the second, okay, plus the derivative of the second cross with the first. Okay. Any questions there? And then the last rule we have is dealing with the chain rule. So with the chain rule, we're taking the derivative in respect to t of a function, a vector function defined as so. So we have the derivative of the inside times the derivative of the vector function evaluated at the inside. Okay, so traditional way you think of the chain rule, nothing different. Any questions? Okay. All right, and then the last thing is dealing with this and says if R is a differential vector function of t of constant length, then if you take the vector function dotted with its derivative, it's going to be equal to 0. Any questions? Okay, so let's work through the examples. So let me switch screens. Okay. All right, so dealing with the first example. All right, so in the first example, we are being asked, we're told that RT is a position of a particle in the xy plane at time t. Find an equation in x and y whose graph is the path of the particle. Then find the particle's velocity and acceleration vectors for the given values of t. Okay, so if we take a look at this, all right, so for the first one, we have that r of t is equal to t squared plus 1 in the I direction plus 2t minus 1 in the j direction. And I'm going to go ahead and write out what t is, and t is equal to 1/2. Okay, so basically the first part of this question, what it's asking us to do is to pull out the equations for x and y in terms for the parametric. Okay, so x, if you think about it, x is first, so it also corresponds with the first component of the vector equation, so it corresponds with I. So for this equation, we're going to have that x is equal to t squared plus 1. Now, for y, it's going to correspond with the second component of our vector, which is j. So what will y be equal to? Yes, it's going to be equal to 2t minus 1. Okay. Any questions there? Okay. All right, so we found the parametric equation in terms of x and y. I mean, we found x and y in terms of t. Now, what the problem is asking us to do is to write it as an equation where x equals or y equals. Okay, so basically we want just x and y's, no t's. So if we do that, essentially what we're going to do in this case, we're going to do a substitution. So I'm going to take this expression and plug it in for t. So what I'm going to have is x is equal to, in place of t, I'm not going to put that. That's bad. I said that's so wrong. I'm going to take the second equation. And what I'm going to do is solve for t and then plug in. Let's back up a little bit. So if I solve for t here, I'm going to end up with y minus 1 divided by 2, y plus 1, divided by 2 equals t. So now I'm going to take this and plug it in for t. So if I do that, I'm going to end up with this. X is equal to y plus 1 over 2 squared plus 1. So x is going to be equal to, this is going to end up giving me 1/4 times y plus 1 quantity squared plus 1. So now I'm just going to clean this up. So it's going to be 1/4 times y squared plus 2y plus 1 plus 1. Or we're going to end up with 1/4 y squared plus 1/2 y plus 1/4 plus 1. Or our equation is going to be 1/4 y squared plus 1/2 y plus 5/4. And this will be our equation in terms of just x and y. Okay. Any questions? Okay, so that's the first part of the question. So next, we want to find the velocity and acceleration vectors at the given time of t. Okay, so if we take a look at that, all right, so we know that RT is defined as t squared plus 1 in the I direction plus 2t minus 1 in the j direction. So our velocity vector, which will be the first derivative, is going to be 2t in the I direction plus 2 in the j direction. Our acceleration vector is going to be the derivative of that, which is going to be 2 in the I direction. Any questions there? Yes. So you have to remember acceleration vector is just a derivative of the velocity vector. Okay. All right, so the other thing is just to find out what the vectors would be at the given time. So v of 1/2, okay, so the velocity vector at 1/2 is going to be 1 in the I direction plus 2 in the j direction. Now, the acceleration at 1/2 is just going to be 2 in the I direction. Okay. Any questions? Okay. All right. So next, let's take a look at what we're going to have. Right. So for the next example, we have this. We have that r of t is equal to cosine of 2t in the I direction plus 3 times the sine of 2t in the j direction. And it's not equal to, but we have the value at t equals 0. Okay, so the first part is that we want to come up with an equation in terms of just x and y. Okay, so first we're going to define x and y in terms of t. So if we do that, what's x equal to? Okay, so we're going to have the cosine of 2t. And what's y equal to? Yes, so it's going to be 3 sine of 2t. Okay, so in the case of this particular problem, it's going to be a little bit harder for us to solve for t and then substitute in, because that's going to introduce inverse trig, and it's going to be really hard to deal with. So we're going to look at it in a different approach. Okay, so what we want to do is we want to get the trig expressions by themselves. Well, if we take a look at this, for x is the trig expression by itself. So for the way x is defined, is the trig portion by itself. Yes. Okay, now for the y, is the trig by itself? No. So what can I do to get the trig by itself?
Divide by 3.
Okay, so I'm going to do that. So for the second part, I'm going to divide by 3. Okay, so what I'm going to do now is I'm going to use something in trig that's going to allow me to get rid of the trig. Okay, now I've got a relationship between sine and cosine, and it's an identity. So what identity can I use to get rid of sine and cosine? And it's thinking of this in a way that you traditionally don't think of it, of getting rid of it.
The Bell-Angle formula.
Say it again.
I mean, the Bell-Angle formula. No.
No. Something even nice is way nicer than that. I don't want to do any inverse cosine or nothing like that. I don't want to use tangent. Okay. Keep in mind, I want to use an identity that is going to produce a number.
Would it be cosine squared plus sine squared equals 1?
Right. Okay. So what we're going to do is use a Pythagorean identity. Okay. Well, if we look at this, it's not quite in the form that we can use the Pythagorean identity, but I can make it easily by squaring both sides. Okay, so if I square both sides, the top one becomes x squared is equal to cosine squared of 2t. If I square the second one, it's going to become y squared over 9 equals sine squared of 2t. Now, what do we have to do in order for that to be equal to 1?
Put them together.
Yeah, we're going to add them together. So, essentially what I'm going to do is add up everything on the left. If I do that, I'm going to end up with x squared plus y squared over 9, and that's equal to, well, cosine squared of 2t plus sine squared of 2t is just going to give us what? Yeah, it's just going to give us 1. So there's our equation. Okay. Any questions? Okay, so we're a little bit past 12, so I want to give everyone a little bit of break. So let's do a 7-minute break and come back at 12:13, and we'll continue pick up on this problem and continue on. Okay. Okay, so let's continue on. Any questions? Okay, so let's I'm going to move to a new page to make sure I have enough room. So we have our position vectors defined as r of t is equal to the cosine of 2t in the I direction plus the sine of, 3 sine of 2t in the j direction. So our velocity vector, okay? So if we take a look at this, what is going to be the derivative of this first component?
Negative 2 sine t in the n direction.
Okay, so negative 2 sine of 2t in the I direction. And then what is going to be the derivative of the second component?
Just cos 2t in the j direction.
Okay, so 6 times the cosine of 2t in the j direction. All right, any questions there? Okay, so for the acceleration vector, so what is the derivative of the first component here?
Negative 4 sine 2t.
It's not going to be sine.
Oh, sorry, cos, I mean.
Yes, it's going to be cosine in the I direction. All right, and what's going to be the derivative of the second component?
Negative 12 sine 2t.
In the j direction. Okay, any questions there? Okay, so what we're going to have is, all right, so our velocity vector at 0, when t is 0, is going to end up being just what?
One. Oh, sorry, remember. Actually, it's 4. No, sorry. Negative 2, 6
So it's
j.
going to be 6 in the j direction.
Sorry, I forgot about.
Okay, so let's keep in mind if we put in 0 for t for this, the sign of 0 is 0. This makes this whole thing 0. So I component is gone. 0 here is going to be 0. Cosine of 0 is 1 times 6 is going to give us 6 in the j direction. Okay. All right. And then if we look at the acceleration at 0, we're going to end up with the value of what?
Negative 4i.
Okay. So negative 4 in the I direction. Right. Any questions? Okay. All right. So next, let's look at our next example. So in our next example, okay. In this case, we are told that our position vector is defined as 4 cosine of t over 2 in the I direction plus 4 sine of t over 2 in the j direction. Okay, and basically what we want to do is to find the we want to find the velocity vector and the acceleration vectors at those times that are given. Okay, so let's start off first and let's find the velocity vector. So v of t is going to be equal to what? So what's going to be the first component?
Negative 2 sine t over 2i.
So negative what?
2
Okay, so negative 2 sine
t over
of
2.
t over 2 in the ith direction. Okay. And then plus the second component is going to end up being what?
2 cosine t over 2.
In the j direction. Okay. And now let's go ahead and do the evaluation. So we're going to look at v of pi, and then we're going to look at v of 3 pi over 2. Okay. So v of pi is going to end up giving us what? Yes, negative 2 in the ith direction. Okay. And then v of 3 pi over 2 is going to end up giving us, so we're going to be dealing with the sine of 3 pi over 4. So that's going to be square root of 2 over 2 times negative 2. So we're going to end up with negative square root of 2 in the ith direction. Plus, then we're going to have cosine of 3 pi over 4, which is going to be negative square root of 2 over 2, which is times 2. So we're going to end up with minus the square root of 2 in the j direction. Okay. Any questions? All right, so next, let's find the acceleration vector. So if we find the acceleration vector, we're going to end up with negative cosine of t over 2 in the ith direction minus sine of t over 2 in the j direction. Any questions there? All right, so let's find the acceleration at pi and at 3 pi over 2. So at pi, we're going to end up with, we're going to have cosine of pi over 2, which is 0, and then the sine of pi over 2, which is 1. So we're just going to end up with negative j. Okay. Any questions? Then we're going to plug in 3 pi over 2. Cosine of 3 pi over 2 over 2 is 3 pi over 4. So the cosine of 3 pi over 4 is going to be negative square root of 2 over 2. And then negative in front. So we're going to have the square root of 2 over 2 in the ith direction. And then we're going to have 3 pi over 4 again for the angle. The sine of 3 pi over 4 is the square root of 2 over 2. Then times negative 1. So minus square root of 2 over 2 in the j direction. Okay. Questions? All right. Any questions? Okay, so for our next example, we have, we're given the position vector in space of a particle. Find the particle's velocity and acceleration vector, then find the particle's speed and direction of motion at the given time t. Write the particle's velocity at that time as a product of the speed and direction. Okay, so in this example, first part, we are told that our position vector r of t is equal to 1 plus t in the ith direction plus t squared over the square root of 2 in the j direction plus t cubed over 3 in the k direction, and we're told that t is equal to 1. All right, so if we take a look at this, we're going to, let's find the our velocity vector. So v of t, all right, so the first component's going to end up being what?
Just 1.
Okay, so we're going to have 1 in the ith direction
Yes.
plus, what's going to be the second component?
2t.
Careful.
Sorry.
Yeah. So it's going to be 2t over the square root of 2 in the j direction. Okay. Plus, and what would the third component be?
T squared.
Yes. So it's just going to be t squared in the k direction. Okay. All right. So now let's go ahead and find the velocity at t equals 1. So our velocity at t equals 1 is just going to be 1 in the I direction plus 2 over the square root of 2 in the j direction plus 1 in the k direction. We can put the 1 or you don't have to put the 1. It doesn't really matter. Any questions? Okay, so next, let's find the acceleration vector. So for the first component, we're going to end up with what?
0.
Okay, so we just leave that off. Second component, we're going to end up with what?
2 over root 2. Square root 2. I mean,
The I direction plus, and then for the last component, we're going to end up with what?
2t.
2t in the k direction. There we go. All right, so if we take a look at the value of deceleration at 1, so if we plug in 1, so for the first component, in this case, which is j, we're going to have 2 over the square root of 2 in the j direction plus for the second component, which is k, we're going to have 2 in the k direction. Okay. Any questions there? Okay, so that is going to be the first part. So continue on with the problem. The next piece that we're asked to do is find the velocity, find the speed. Okay, so at the given time. So we're going to look at the magnitude of the velocity vector at 1. Okay, so we're going to end up with the square root of 1 squared plus 2 over the square root of 2 squared plus 1 squared. So we're going to end up with the square root of 1 plus this piece here. It's going to be 4 over 2, or just 2 plus 1. So we're going to end up with a value of 2. Any questions? Okay, so next we're going to deal with the direction, and we're dealing with the direction of the direction of motion. So we're dealing with the velocity. So we're going to take the velocity vector, evaluated at 1 over its speed. Okay, so we found the speed to be 1/2, and then the velocity vector is 1 in the I direction plus 2 over the square root of 2 in the J direction plus 1 in the K direction. Any questions? And then the last thing that we had to do for this problem is to write the particle's velocity in terms at the time in terms of the product of speed and direction. So the speed, which is 2, the direction, essentially what we would want to do is just multiply this out. So if we do that, we're going to get 1/2 in the I direction plus 1 over the square root of 2 in the J direction plus 1/2 in the K direction. And that would be the velocity represented in terms of speed and direction. Any questions? Okay, so let's move to the next example. All right, so in the next example, we are given the position vector in space of a particle. Find the particle's velocity and acceleration, and then find the speed, speed and direction in motion, and then write the particle. Okay, so we're still doing the same one. Same thing, we just got a different function. So my eyes got crossed. Sorry about that. So our second example, same direction. We're given that the position vector is giving us as e to the negative t in the I direction, plus 2 times the cosine of 3t in the j direction, plus 2 times the sine of 3t in the k direction, and we're told that t is equal to 0. Okay, so what I want you to do real quick is to find the velocity and the acceleration vectors. Okay, so find the velocity and acceleration vectors. Okay, so let's see what we got. So for the velocity vector, you should end up with negative e to the negative t in the I direction minus 6 sine of 3t in the j direction plus we're going to have 6 cosine of 3t in the k direction. For the acceleration, we should end up with e to the negative t in the I direction minus 18 cosine of 3t in the j direction minus 18 sine of 3t in the k direction. Okay. Any questions there? Okay, so let me find the each of those vectors at time 0. So the velocity vector at 0 is going to give me -1 in the I direction, sine 0, 0, so there's no j component, but there is a k component, and it has a coefficient of 6. Then for the acceleration at 0, we're going to have 1 in the I direction. We're going to have -18 in the j direction. The sine 0, 0, so we have no k component. So this is your velocity and acceleration vectors for this. Any questions? Okay, so next we are asked to find the speed. I've got a little bit of room here, so I'm going to do the speed here. So it's going to be the magnitude of the velocity vector at 0. So we're going to have the square root of 1 plus 36, or the square root of 37, and that is going to be our speed. Any questions? Okay, so next we need to do direction. So basically the direction is doing a unit vector. So we're going to look at the velocity at 0 over the magnitude of the velocity at 0. So we're going to have 1 over the square root of 37 times our vector, which is going to be -1 in the I direction plus 6 in the k direction. And then the last thing we have to do with this problem is deal with the direction. Okay, so it wants to write it in terms of speed and write the velocity vector in terms of speed and direction. Sorry. Oops, wrong color. Right color. Okay, so we're going to write the velocity vector as a product of the two. So we're going to take the length, which is the speed, which is the square root of 37, times, then this is the direction portion. So we're going to have -1 over the square root of 37 in the I direction, plus 6 over the square root of 37 in the k direction, not j. Any questions? Okay, so for today, I'm going to stop here. I still got 2 more examples to finish up for this section, but I'm going to go ahead and stop so that I don't feel like I'm rushing through these last 2 examples. Okay. All right. So you need to make sure that you work on the homework over cylinders and quadric surfaces. Okay. And again, for that section, I will display all the graphs of these for you guys on Thursday in class. Okay. As far as the simplification, no, I don't care about you rationalizing the denominator. Okay, so if you leave a radical in the denominator, it's completely fine. Any other questions? Also, a reminder, if you haven't submitted your quiz 2, you need to do that by 2 p.m. Okay? All right, you guys have a great rest of your day, and I'll see you on Thursday.